Hello everyone. So let's finish up this module of scales of turbulent motion. We were discussing the energy spectrum balance in last class and we couldn't finish it up. So let's complete the analysis here. So again, just to cover what we were just talking about towards the end of last class, this is the energy spectrum balance. It's a balance equation for the energy spectrum, as in the 3D energy spectrum, which is E of kappa t, and kappa is the wave number magnitude. So the time derivative of the energy spectrum function, as in the rate of change of the energy spectrum with respect to time, that is what forms the balance equation for E of kappa t. Now on the right hand side you have three terms. The first one is the production term, the second one is the spectral transfer, and the third one is the dissipation. So essentially this makes up for the three regimes in your energy cascade, isn't it? You have the energy containing range, so that's where the energy is produced, the production term. You have the inertial range through which there is a transfer happening, okay? And then you have the dissipation range where the actual dissipation of turbulence is happening, and that is what this term is. This is essentially the D of kappa t. We had plotted even the dissipation spectra from the model spectrum. So what is the production term, right? So the production term is given by the product of this mean velocity gradients and an anisotropic part of the spectrum tensor. Let's not get into that. In fact, let's just think of it as the range where the wave numbers where energy is being produced. So if you think about the contribution to the production from the wave number range, that is denoted by P of kappa A kappa B, which is the integral of kappa A to kappa B, the P kappa of P kappa dk. So you are integrating the production spectra over a range of kappa A to kappa B, and that is the contribution to the production in that wave number range. Isn't that clear? So then you have the second term, which is the spectral transfer rate. Now if you integrate that, okay, so the spectral transfer rate, if you notice here in the energy spectrum balance equation, the first term on the right hand side is the production term, the second term is the spectral transfer, and the third term is the dissipation, isn't it? But the second term is slightly different. It looks slightly different from the first and the third term. The second term is a derivative with respect to wave number. That is because it has to do with the rate at which energy is transferred with respect to wave number. It is dependent on the wave number. It goes from the large scales to the small scales. Energy transfer is from the small wave numbers to the large wave numbers. So there is a derivative that would be in there. Now it is basically the net rate at which energy is transferred from the modes of the lower wave number to the modes of the higher wave number. That's what it is. So if you want to find out the rate of gain of energy in the wave number range of kappa A to kappa B, you basically integrate this term, isn't it? So that is what is shown here, kappa A to kappa B minus del K, because that term itself has a minus, and TK dk. All right. So now you are integrating a derivative. If you integrate a derivative, you will basically get the function you were taking the derivative of itself. So that is what you're getting. You're getting Tk of kappa A minus Tk of kappa B. Now, one thing I wanted to point out even the last time is that why do we have a negative here? Because you are going from smaller wave number to higher wave number. So because of that you have a negative. It is not going from larger to smaller. You're going from a smaller wave number to a larger wave number, so you have a negative there. As a result of which, once you integrate this, you will get Tk of kappa A minus Tk of kappa B. So basically the difference of the two endpoints. Now from this we realized that since Tk is vanishing both at 0 and infinity wave numbers, why is that? It is vanishing at 0 wave number because nothing below it, isn't it? There's no energy to transfer from below that wave number, so it is 0. And at infinity wave number, it is also 0 because there is no energy to there is no wave numbers to transfer the energy to from there. That's the largest wave number. So at both ends, it should be 0, isn't it? So that much we know. Finally, the third term, which is the dissipation spectrum, so that is d of kappa t, as I was saying earlier, 2 nu kappa squared E of k t. Now for looking at what the plot looks like. So I'm just going to erase this and look at this again. So I'm not able to erase it, but then let's see what it looks like. So I have the E of kappa on the left hand side, right? So the first figure is what it is showing me is, as in figure A, it is showing me I have E of kappa being more dominant in the energy containing range, which actually becomes the dissipation spectra being more dominant in the dissipation range. So I have three ranges here, isn't it? I have the energy containing range, ER, I have the ISR, which is the inertial subrange, and I have the dissipation range, which is the DR, isn't it? So these three ranges, you can see how each one is dominating. The E of kappa is more dominant in the energy containing range, whereas the dissipation spectra is more dominant in the dissipation range. We knew that already. This makes sense. The production is more dominant in the energy containing range. Yes, because the energy is being produced there. And I brought out examples last time when I talked about a jet flow and flow coming in through the nozzle. That is what is bringing in the energy, correct? So then I have the production being more dominant in the energy containing range. Then there is this additional term, so the spectral transfer term, as in the spectral transfer rate term, minus del T del K, minus del T del K, that exists everywhere, right? That exists everywhere, as in what is happening is that del T del K is going to be, as in minus del T del K is going to be negative in the energy contained range, because the energy is being removed out of the large scales. Because the energy is being removed out of the large scales. And the minus del T del K is going to be positive in the dissipation range because energy is being received from the large scales onto the small scales. So it is being received here. Now this minus del T del K is sort of flat-lined, is almost zero in the inertial subrange. That is because if you actually take the energy transfer rate, okay, it starts increasing from zero, and we know that it increases from zero because there is nothing below it, isn't it? Nothing below the lowest wave number of zero. So it would start from zero. It has only one way to go but up. So it will keep increasing, and then it flatlines in the inertial subrange, and then it slowly decreases as the energy is being dissipated out. So it slowly decreases. Now here what will happen is, because if you look at TK, it is almost a constant here. Over the inertial subrange, it is almost a constant. So that is what is leading to this minus del T del K being zero here. I hope this makes sense. So we looked at the production, we looked at the dissipation. Another one additional thing that I want to point out is this minus D here, which is the actual dissipation. So you have production on being dominant in the energy contained range, and then dissipation being dominant in the dissipation range. And this transfer starts from zero, plateaus out in the inertial subrange, and then keeps decreasing in the dissipation range. So I hope this was clear. Now let's take each range and try to integrate the energy spectrum balance equation for each range one by one. In the energy contained range, all the terms are significant except for dissipation. What do I mean by that? Production is significant. Transfer is also significant because energy has been removed out of the large scales. But there is almost no dissipation. In that sense, if you take the turbulent kinetic energy in that range, 0 to kappa EI, it would be approximately equal to K itself. The dissipation over that range is going to be equal to 0. And the production over that range is going to be equal to the total production. The Tk of kappa EI is going to be TEI because T of 0, Tk of 0 is 0, as I was pointing out last class. So when integrated over the entire range, as in from 0 to kappa EI, what you get from the spectrum energy spectrum balance equation is that you will get dk dt is approximately equal to P minus TEI. All right. Then go to the next one, the inertial subrange. The spectral transfer here is the only significant process. You have accounted for all production. Dissipation is mostly significant only in the dissipation range. So spectral transfer is the only significant term. So now when you integrate your energy spectrum balance equation, left hand side becomes 0, and then you have only the spectral transfer rate, which is TEI minus TDI, isn't it? It will be TEI minus TDI, basically the two endpoints. The first endpoint minus the second endpoint. The initial endpoint minus the final endpoint in the inertial subrange. That is TEI minus TDI. Okay? Then finally, the dissipation range. Here, only dissipation is significant. Of course, spectral transfer is also significant. So, what I mean is, turbulent kinetic energy is not dominant, is negligible. Production is negligible as well. So you have 0. Production term goes to 0, and then as far as the spectral energy transfer rate is concerned, since T of infinity is 0, so T of kappa infinity is 0, isn't it? So because it is at infinity is equal to 0, all you have is TDI minus epsilon. Now if you add all of these three equations, what you get is dk dt is production minus dissipation. That's it. So the transfer doesn't matter in the overall scheme of things. Over the overall wave number range, the transfer doesn't matter. It is either production or dissipation. So the rate of change of kinetic energy is the net production minus the dissipation. The net production minus the dissipation. That's what it is. All right. So now that we have covered the spectrum energy balance equation, all that is great. We looked at the Kolmogorov hypothesis, we looked at the model spectra, we looked at how the Kolmogorov hypothesis applied to the model spectra, how we got different terms in the model spectra and how they behaved, the dissipation spectra, the kinetic energy, the cumulative dissipation, the cumulative kinetic energy. We saw where most of the energy was concentrated in. We saw where most of the dissipation was concentrated in. While doing all of this, we always made it a point to say that all of this is valid only when the Reynolds number is high enough, right? We never quantified what that high enough means. How high should it be? Should it be 10,000? Should it be 100,000? Should it be 1,000,000? Okay, so this is an interesting scenario. This is the plot of the P value. What is the P? P is basically the energy spectrum varies according to kappa to the minus P. We know that in the inertial subrange, P is minus 5/3, isn't it? If you had your spectra, the spectra looks like this. And this was 5/3, as in negative 5/3, of course. So we know that E of kappa is of the scales with kappa to the minus P. That P is minus 5/3, but that is according to the Kolmogorov hypothesis. Now, the fact that it varies according to minus 5/3 is determined by the condition that it is at high Reynolds number. Right? So what is shown here is a spectrum power law exponent of this P. Okay? Well, according to us, it should be minus 5/3. It looks like it is not 5/3, right? So because minus 5/3 is 1.67, 5/3 is 1.67. So here we have the power law exponent P as a function of the Reynolds number in grid turbulence. The symbols are experimental data from 1998, and the dashed line is the value of P is equal to 5/3, so that is where it should be. And the solid line is an empirical curve, meaning it's a curve based on the data. Okay, it's a curve fitting based on the data. So this is what the data is showing. As you can see, if I have a R lambda of approximately 100, my P values are like 1.3 and 1.4, not close to 1.67. As I'm getting to a Reynolds number of R lambda of, so this is 100, this is 200, this is 300, this is 400. So as I'm getting to a Reynolds number of 400 and 500 and all that, I am getting close to 1.6, not even 1.6. So that tells you that for it to be close to 1.67, 5/3, as we think it should be, the R lambda should be close to a 10,000. Then it will be close to 1.67. So that is how high R lambda has to be. Now, this is a Taylor Reynolds number, R lambda. I understand it is difficult to correlate that with a more realistic Reynolds number, but think we had an expression showing how an integral scale Reynolds number is related to R lambda. We had that earlier. But think of it as if R lambda is around 10,000, the integral scale Reynolds number is about is more than 100,000, is definitely more than 100,000. It is close to a million or so. But we'll have to look at that equation to get the exact number. But it's a very, very high Reynolds number. So that means to get to a p-value of 1.67, we will need to get to a really high Reynolds number. And that makes sense. That's the reason why even when stating the Kolmogorov hypothesis, we always made it a point to say that at high enough as the Reynolds number, if the Reynolds number is high enough. So that's the point we are trying to make through this figure. So the notions of the energy cascade, vortex stretching, Kolmogorov hypothesis, obviously they provide an invaluable amount of data and concept, right? But both conceptually and empirically, there are shortcomings to it. It should still be noted that even with these limitations, they do give us a lot of information on how turbulent flows should be modeled. Because so essentially what we are trying to say is they don't have a major impact on some of our understanding, but it is important to be aware of these limitations, of these shortcomings. Only then some of these models can be improved. And the reason why we say that is, and that has to do with when we looked at this cumulative turbulent kinetic energy, we noticed that 80% of the energy is contained in the energy containing range. 80%. The only 20% is in the very few scales below that, even at the smallest scales, and mostly 10 to 15% of the energy is contained in the dissipation range. Isn't it? So because the small scales contain very little energy, they have little direct effect on the flow. Okay, they have little direct effect on the flow. So whatever we are saying, even though there are some shortcomings, making some assumptions is giving us a lot of information, is helping us move forward. So one of the limitations of the Kolmogorov hypothesis, as I was saying earlier, is it applies only to high Reynolds number flows. But a criteria for high Reynolds number is not provided, right? So, for example, many laboratory or practically flows have reasonably high Reynolds number. So that, see, this is what I was talking about earlier. R lambda of 150 is like an RE of 10,000. So R lambda of 10,000, or in fact, not 1,000, but 10,000, right? 10,000 would be an extremely high Reynolds number. And sometimes you don't even get to that Reynolds number before you apply the Kolmogorov hypothesis. So that's a limitation. You should know that that exists, but it doesn't seem to be affecting our predictions, our understanding of the problem as much. Okay, and that is because of these dissipative scales which don't contain as much energy. That is the reason why it is not affecting our predictions of the problem. So that is pretty much what is described in this slide in more detail. So on closely looking at the inertial subrange spectra, the Kolmogorov minus 5/3 spectrum is slowly approached as RE increases. So from experiments on grid turbulence, the inertial range spectrum is indeed a power law, but that exponent depends on RE lambda. So P does approach 5/3 at very large RE lambda, but at RE lambda is equal to 200, for instance, P is 1.5, right? All the experimental data considered so far pertain to second order statistics, as in statistics that are quadratic in velocity. Now, this is another limitation. We always look at variance. At the most we go to variance. But what about third order statistics or fourth order statistics? Now, isn't that something to be looked at? So that is where it takes us to things like velocity derivative skewness or velocity derivative kurtosis. So I'll describe that before I come to this plot. The simplest example of a higher order statistic is this velocity derivative moments. Okay, calculated as mn is del u1 del x1 to the power of n divided by del u1 del x1 squared average to the power of n half. Okay, so if n is 3, you have a velocity derivative skewness. If n is 4, you have a velocity derivative kurtosis. This is your third order moment and your fourth order moment. This is a simple higher order statistic to be looking at. For a Gaussian distribution, for instance, this skewness and kurtosis have fixed values. For a Gaussian random variable S, the skewness is 0 and the kurtosis is 4. How close to 4 do you get when you do the velocity derivative kurtosis for a turbulent flow? Definitely it's not going to be 4 because the turbulent flow is not Gaussian. Now, according to the Kolmogorov hypothesis, we did not cover that a lot but Mn is a universal constant. Even the third order moments and the fourth order moments would be the same. However, it is found that S and K are not constant and they increase with Reynolds number. So we don't see S and K being a constant, but according to the Kolmogorov hypothesis, Mn is a universal constant. In contrast to the RE-effects that we had discussed, K does not appear to be an asymptote. Instead, data are consistent with an indefinite decrease. As you can see in this plot, this is the kurtosis that is plotted with R lambda. As you can see, they are continuously increasing. These symbols are measurements. These are experiments coming. Different kinds of experiments, squares, triangles, solid circles, solid triangles, all shown here. And if you see a trend line, a curve fitting line here, that line is continuously increasing, right? So the solid line is K is R lambda to the 3/8. So it fits with that kind of trend line where with increase in lambda, you are seeing an increase in kurtosis. And that is what is happening. In fact, but according to the Kolmogorov hypothesis, this K is supposed to be a constant, like it is for a Gaussian. Is that the actual scenario? No, it is not. So these discrepancies between the Kolmogorov predictions and the experimental values of higher order moments are attributed to what is called internal intermittency, which is a whole different scenario to be looked at, and we are not covering that in this class, but it is attributed to internal intermittency. Again, it should be emphasized that in the context of the mean velocity field and the Reynolds stresses, these issues are of relatively minor significance. The turbulence energy and anisotropy are predominantly contained in the large scale motions. So as long as you are covering that, then you are okay. Internal intermittency, on the other hand, concerns rare events that only manifest in the higher order statistics of small scale quantities. We only see that in the small scale quantities. Even if you are not covering it as much, because most of the energy is contained in the large scale motions, it is not affecting our predictions as much. So in the context of this energy cascade and turbulent flows, the internal intermittency of more importance is the question of what determines the energy cascade from the energy containing scales rather than the internal intermittency. But that said, it is important to be aware of what the limitations are. When we talk about the Kolmogorov hypothesis, we say it applies at higher Reynolds numbers. How high should the Reynolds number be? And how close to the Kolmogorov spectra slope of 5/3 do we get to when R lambda is say 200? When R lambda is 500? We are not approaching 5/3 yet. It is important to be aware of that particular limitation. The other limitation is related to the kind of moments that we take. We always limit ourselves to second order moments, variances, isn't it? Variances, we stop there. Now, when should we look at even higher order moments like velocity derivative skewness and velocity derivative kurtosis? And this was one figure that was showing how the kurtosis is different here from what Kolmogorov hypothesized. So that is why typically when we run computations and try to compare it to experiments, sometimes you compare the mean alone and you say, okay, I have got great predictions. Does that mean my model is correct? If you compare variance and variances are also reasonably predicted well in comparison to experiment, do you say your model is correct? Maybe you can go a step further and compare your velocity derivative skewness and velocity derivative kurtosis to experimental data if they are available to see how closely do they match. And then you start to make some progress in saying, okay, I'm doing something right in my model, or to even look at how does the kurtosis vary with an increase in Reynolds number. Try two different Reynolds numbers to see how the kurtosis varies. Does it change? Does it increase? Or does it stay constant? That would give you an idea of how well the model is. So this module covered a lot of different things. We started by talking about the velocity spectrum tensor. Then we went on to describing the energy spectrum function. We talked about the 1D spectra, how the spectra vary. We looked at different kinds of scaling. We normalized it to see the universality of the spectra. As much as we covered theoretically through the Kolmogorov's hypothesis about the universality of the universal equilibrium range, for instance, how it stayed universal as long as it was scaled. We saw that quantitatively and even figuratively by looking at the energy spectra function and scaling it right way when we saw different curves overlapping onto a single curve, demonstrating the universality of that particular range. And then we focused on the energy containing range separately, the inertial range separately, and the dissipation range separately, and tried to analyze how these would behave under different conditions. So a very detailed module where it took us a few classes to cover this, but we have covered, we have looked at different scenarios here, and finally we wrapped it up with looking at the limitations of the Kolmogorov hypothesis in terms of looking at actual experimental data and how they behave vis-a-vis the Kolmogorov hypothesis. So I hope this was clear. We'll go into the next module in the next class. Thank you.